Hello, this is Ms. DB, and today we're going to talk about how to solve a linear system when there's three variables. Generally, that's an x, y, and a z. So we are going to say how those solutions of equations might look graphically, although we're not going to graph them, and then we'll solve them using algebra. All right, so when there is, you know what an xy coordinate system looks like. When you have a third variable, that generally means that you have a three-dimensional system. Some of you who have done gaming or have done any digital animation are probably familiar with the z-axis. Others of you maybe not so much. But when we have a xy system, coordinate system, where x is the horizontal and y is the vertical, this is a two-dimensional flat coordinate plane, like a tabletop. If we add in a third axis, now our two-dimensional system becomes a three-dimensional. If you were going to sketch it, it generally looks like this. Rather than x and y being drawn perpendicular to each other, they of course still are perpendicular, but you would draw them as at an angle, and then the z is generally drawn as the straight up and down vertical one. It's just the way it typically is done. It's a little bit tricky to do this by hand. We are not going to do this by hand. You can find some good programs, like I talked about, some digital animation, where you can picture this and see this better. The origin is still right here. The origin would be 0, 0, 0. A point in the coordinate plane will be x, y, and then z, z being that third dimension. So in 3.5, which we're skipping over, this one was about how to draw points, graph points, and draw lines in three-dimensional space. But like I said, we're not going to do this one. But here's an example of what you would do. So first of all, you have to draw your x, y, and your z axes. And then from the origin, which of course is here, you move along the x-axis, which it's important to label these, 3 units. And then you move -2 left, because we're going to -2 on the y, so 1, 2, and then we would go up 1 unit because our z is now on the, well, vertical to us in 2 dimensions, and we would move 1 up, and then this would be our point right here then. It's quite tricky to picture for many of us how that is in 3-dimensional space, but with shading and such, there's ways to make it look a little more 3D. All right, if you are going to graph a linear equation like y equals 2x plus 3, it's a straight line. In 3-dimensional space, the graph of a linear equation is a plane. So because a plane is defined by 3 points, that's a definition from geometry. If you have 3 non-collinear points, not in a line, that defines a plane. You can graph linear equations in 3 dimensions by finding the 3 intercepts. So this is, again, this is from 3.5 that we're not doing, but I wanted to show you a couple examples from it of graphing these. So if you were to graph this 3-dimensional equation with an x, a y, and a z, the easiest way to do that is to find the intercepts. So the x-intercept is when the y and the z are both 0. So we can find the x-intercept by letting y and z be 0, and then we would get this. And then we can find the y-intercept by letting x and z be 0. This was our x and this was our z, and solving the little equation that results. And then we can find the z-intercept by letting x and y be 0. The result is 3 intercepts, and you can put those 3 intercepts, here they are. This was the x-intercept, this was the y-intercept, and this was the z-intercept. You sketch them on this xyz coordinate plane. So the point -3, 0, 0, this one might be the most complicated. This is the positive side of the x, and this is the negative side of the x-axis. This is the positive side of the y-axis, and this is the negative, and this is the positive z, and this is the negative. the positive x is coming towards us. So it makes sense then to see that the negative would be going back away from us. So you would put those 3 points on the axes and then draw this plane between them using this kind of triangular shape, and then attempt to shade in the region that would contain that plane. Quite tricky, actually, to do by hand. Those of you who are good at drawing or are used to 3D figures can probably do that better. All right, now we're going to be moving on to how to solve these algebraically. That's what the bulk of this lesson is on, and that's what your worksheet will be on. All right, so we know that the graph of a linear equation in 3 variables is a plane. We just looked at that. When you graph a system of 3 equations in 3 dimensions, the result is 3 planes. So remember how this went. Picture 3 planes in that system, on that same coordinate system. That's what we're going to be looking at today. And you can see that graphing those 3 planes would be a little bit tricky to see what the solution was. A little tricky just to graph them in the first place. So there's different options or different things that can happen when you graph 3 planes. You might have no solution. Now, a solution to a system is when there is an intersection of all 3. So the solution has to be the intersection of all 3 lines or all 3 equations. It's planes, intersection of all 3 planes. And the plane is named by its 3 equations, I'll say. Now, in this first one, all the planes are parallel. They'll never intersect, and there is no solution. In the second example, the green plane and the blue plane intersect along this line. The intersection of 2 planes is a line, but the blue one never intersects the red one, so that's not a solution. And the third one, they form this, there's an intersection here, there's an intersection here, and there's an intersection here, but there's no place where all 3 planes intersect. So before I turn the page here, think about how could I show all 3 planes intersecting? What would that look like? So all of these, every one of these, if you were to solve and get a picture that looked like this, if you were going to try to sketch it, you would say no solution. All right, so here is when you can have solutions. You can have one solution. This is going to be the first 4 on the worksheet, where we're going to find one coordinate point, x, y, z, where all 3 planes intersect. So look, this is a visual of what our point would be showing us, where those 3 planes are intersecting. We could also have this. We could have the 3 planes intersecting at one line. So there's infinitely many solutions because every point along this line, so it's not every point in the world, but every point along that line, that x, whatever that equation is, that would be a solution to this system. So those are our 2 times where we can have solution. And again, this is what we're going to be looking at first, when there is one solution in an independent system. We're going to be using elimination mostly to solve algebraic. You can also use substitution. Most of ours are going to be set up for elimination. And what we're going to do basically is first take your 3 equations, because that's what it's going to be. It's going to be 3 xyz equations. And we're going to first try to figure out how we can change them so that we can get 2 equations. So maybe we can add 2 of them together to eliminate one of them, to eliminate one of the variables. Like in this example, if I added the bottom 2, I would eliminate the z term. And then you'll do something to 2 other ones to get another z term eliminated with 2 other combinations. And then once we have 2 equations, 2 unknowns, we'll just use the methods that what we learned about last week. In general, to find a single solution to any system of equations, you need as many equations as you have variables. So last week we looked at if you have 2 variables and you have 2 equations, what is the solution? This week we'll look at 3 equations, 3 variables. You could also solve 4 equations with 4 different variables. We're not going to, but you can. All right, so here's our first example, and this is an example from your worksheet. On your worksheet, if you don't show your work, you don't get any points. Now, it's kind of hard to type all of this up. If you don't want to type, write your work on notebook paper, take a picture with your camera or your phone, and attach it digitally. Take a screenshot, paste it into your worksheet, whatever you need to do. So there is calculators out there on the internet that will find this answer for you if you just type them in. I know that. We're not aiming at trying to find the answer. We're aiming at going through the steps to find the answer. There's only 8 of these on your worksheet, and I'm going to do several of them in this video. So, all right, so first of all, what we want to do is figure out, is there a way to eliminate one of the variables right away so that we would have less to work with. So we have 2x minus y plus z equals negative 3. I'm going to call this number 1. Sometimes it helps to talk about these as, the first equation, second equation, and so on. But I'm just going to name this as equation 1, and then I'll name this as equation 2, and this is equation 3. All right, so equation 1 has a positive z, equation 2 has a negative z. I can add those two together right away. Now, why did I do that? I did it to make a simpler equation. I will no longer have the z term. That's simpler. That's how we start. We start by looking for ways to make it simpler. 2x plus, and I'm using elimination, 2x plus 1x is 3x, minus 1y plus 2y is 1y, z minus z is 0, cancel, gone, negative 3 plus 2 is negative 1. Make sure, double check that you're not making mistakes with your negatives, with your adding, because it'll mess everything up and this will be a disaster. So double check that negative 1 plus 2, yep, that's 1. Negative 3 plus 2 is negative 1. All right, so I've got one equation with an x and a y. I need to go back up here. I did 1 and 2 already. I need to combine 2 others, not 1 and 2 again, or I'd get the same exact answer. But I could do 1 and 3, or I could do 2 and 3. I want to pick 2 that would also eliminate the z variable. I guess I'll just use 1 and 3. So here's, let me get a different color. Number 1, and again, I want to also try to get rid of the z term again. It wouldn't do any good to get rid of the y term when down here I have an x and a y. I want them to be the same 2 variables when I'm done. This would be x plus 3y minus 2z equals 3. Now I can't just add them together like I could in the last one. The last one was set up for elimination because I had plus z minus z. This one I have plus z minus 2z. But if I multiply the top one by positive 2, that would work. So if I multiply everything on the top of the first equation by 2, I'll get 2x. Oh, no, I won't. I'll get 4x, 2 times 2, 4x minus 2y, I'm using the distributive property, plus 2z. Now, do not forget to multiply the other side by 2 as well, and you get negative 6. So now my 2 equations are right here. Now I can use elimination to add these together. When I add these together now, I have 1x plus 4x is 5x, 3y minus 2y is plus 1y, the negative 2z or minus 2z plus 2z is gone, 0 cancels, 3 minus 6 is negative 3. So I now have a whole new set of equations. Let me write them. I have 3x plus 1y equals negative 1, and now I have 5x plus 1y equals negative 3. It's almost like we're starting over. We have a new problem to do. This is just like you did in 3.2. You can solve this with either elimination or with substitution. I like elimination, and it's almost set up for elimination, so I'm going to use that. I have a plus 1y and a plus 1y, so if I could just make one of them negative, I'd be good. So I'm going to multiply everything on the top by a negative 1. That gives me negative 1 times 3x is negative 3x. Negative 1 times 1y is negative 1y. Negative 1 times negative 1 is 1. Now I'm going to add these two equations together. 5x minus 3x is 2x. Plus 1y minus 1y is gone. It's 0. Negative 3 plus 1 is negative 2. And then I divide both sides by 2, and I get that x is equal to negative 1. So x equals negative 1. I have my first variable solved for. Once you have what your first variable is equal to, now use one of these smaller equations to find the other one. So I'm going to use the top one. 3x, I'm going to solve for y. So 3x is plus 1y equals negative 1. I know that x is negative 1, so I substitute in and I simplify and I solve for y. Plus 3y or 1y is equal to 2. So far I know what x is, I know what y is. There's one letter left. I need z. And I think I have enough room even. You might think I don't, but I think I do. All right, so for z, I'm going to go back to one of my original 3 equations. Pick the simplest one that you can. I like number 2. Number 2 was x plus 2y minus z equals 2. I know what x is. X is negative 1. I know what y is. Y is 2. I'm trying to find z. So I have negative 1 plus 4 minus z equals 2. And negative 1 plus 4 is 3. So I have 3 minus z equals 2. Am I going to run out of room? Negative z equals negative 1, which means that z is equal to 1. So I have an x, I have a y, I have a z. You'd think I'd be done, but I'm not. I'm almost done. I'm going to check my answer. What I got was that x is negative 1. I got that y was 2, right? Yep, y was 2, and z was a positive 1. You can write that as an ordered pair, except it's an ordered triple, isn't it? Ordered triplet? With just like you would write an xy ordered pair, but with one more, with z at the end. And now we're going to check our answer. Now, why do we have to check our answer? Because look at all the work we did here, and all the negatives, and all the distributive properties. It would be easy to make a mistake. So we are going to check by using this point, this x, y, z, in each of our 3 equations. And I'm going to first do the first one. So 2 times x, but x is negative 1, minus y, but y is 2, plus z, but z is 1. And I want to see if that is equal to negative 3. If it is, it checks, it works. Does that equal negative 3? That'd be negative 5, or negative 4, sorry. Negative 2 minus 2 is negative 4, plus 1. It does equal negative 3. Negative 3 equals negative 3. The first one checks. This one's good. Okay, then I'm going to do the second equation. So x is negative 1 plus 2 times y, that's 2, minus z, which is 1. I want to see if that is equal to 2. So negative 1 plus 4 minus 1, is that equal to 2? Negative 1 plus 4 is 3. 3 minus 1 is 2. 2 equals 2. That one checks. Okay, one more to do. And you do not have to show me the check on your worksheet. You can do that on your own paper. But if you check it, you'll know your answer is right and that you got that problem right. All right, the third one is x is negative 1 plus 3 times y. And y is 2. And z is 1. And I want to see if that's equal to 3. So negative 1 plus 6 minus 2. Does that equal 3? Negative 1 plus 6 is 5. And 5 minus 2 is 3. 3 equals 3. It works. So it worked in all three equations, my point, so then this indeed is the solution to this problem. All right, let's look at this example. We have a little bit more complex equations here, but that doesn't matter. We're still going to do the same thing. I numbered these 1, 2, and 3, so we can talk about them in that way sometimes. It makes it a little easier. All right, so our first step again is to eliminate one of the variables. You have many options for this. We could try to eliminate the x variable. We could try to eliminate the y. We could try to eliminate the z. In this one, let's go with z again. It's not always going to be eliminating the z, but it looks like it's going to be pretty easy to do because we have a 1z in this middle one, and it'll be easy to eliminate from either the top one or the bottom one. So we are going to start by, here's our three equations again. We're going to multiply the second equation by 3. Because the first equation, number 1, was negative 3z, I want this one to be a plus 3z. So here is the number 1 equation just written again, 5x minus 2y minus 3z equals negative 7. Then I take the second equation and I multiply everything by 3. So 3 times, just do the distributive property. So we get 3 times 2x is 6x, 3 times negative 3y is negative 9y, 3 times z is 3z, and negative 16 times 3 is negative 48. Now we're going to add these together. This is elimination. 5x plus 6x is 11x. Negative 2y minus 9y is negative 11y. The z's cancel, like we were hoping, and I end up with equals negative 55. Now we have a new equation. We're calling it number 4. We're going to have this one to work with. But that's not enough. We need 2 equations to work with. 2 equations, 2 unknowns. So I'm also going to work with equation 2 and the third equation. So remember, equation 2 was just the 2x minus 3y plus z equals negative 16. The third equation was 3x plus 4y minus 2z equals 7. So this time, start with your original number 2 equation, and we're going to multiply by 2 so that we can get a 2z plus 2z to go with our negative 2z, our minus 2z from number 3. So here's the number 3 equation just written again. The number 2 equation, I multiplied everything through by 2 to get this. 4x minus 6y plus 2z equals negative 32. And then we add. 3x plus 4x is 7x. 4y minus 6y is negative 2y. The z's cancel like we wanted it to. That's what we were doing. And then 7 minus 32 is negative 25. We can call this number 5 equation. These 2 equations we will now put together in their own system. And we will solve just like we did in 3.2. So we have the 11x minus 11y equals negative 55, and we have 7x minus 2y equals negative 25. It's just the same as what you learned how to do in Algebra 1. So now we can solve with substitution or elimination. And one method of doing this is to get both of our y terms the same. And they decided that 22y would be good. I'm going to do this a little bit easier way. If you notice, the top equation are all multiples of 11. We have 11x, negative 11y, and negative 55. I could divide this equation by 11, which would mean I would divide. You can use the division property. As long as you divide both sides by the same number, it's fine. That would result in the equation, a much simpler equation, of 1x minus 1y equals negative 5. I'm going to work with these 2 equations instead. So now I can use either substitution or elimination. We haven't used substitution yet on these problems, so let's do that. I'm going to solve 1x minus 1y equals negative 5. I'm going to solve that for x. All I have to do is add 1y to both sides. So I would have x is equal to y minus 5. Write it as simple as I can, right? Now, whenever I see an x in the other equation, I will replace it with y minus 5. So the other equation was 7 times x, but x is y minus 5 minus 2y equals negative 25. And then do your distributive property. 7y minus 35 minus 2y equals negative 25. Combine your like terms. And we have a two-step equation. Add 35 to both sides. And y is equal to 2. X now is going to be 2 minus 5. So x is negative 3. So we know what x is. We know what y is. But don't forget, we started with an x, y, z. So we still have to go through and find our z term. Here's one of our original equations. So we take our x of negative 3, our y of 2, and we plug this in, and we'd get negative 6 minus 6 plus z equals negative 16, which is negative 12 plus z equals negative 16. Add 12, and we get z equals negative 4. So then our final thing to do here is write this with all three together in their parentheses, the x, the y, the z, and then to check our answer. And when we check our answer, hold on a second, I'm going to write that on my paper. Negative 3 to negative 4. I'm just going to go back to where we saw our original problem here a while back. This one took a few pages. Here we go. When we check it, this one, the numbers were bigger to start with, so you want to be careful on your check. But our solution that we found was negative 3 to negative 4. So you would put 3 in here, you would put 2 in here, and you'd put negative 4 in here, and you would see if it equals negative 7. Let's just check the first one for time's sake. 3 times 5 is 15. Minus 4, negative 3 times negative 4 would be plus 12. Remember that when you add and subtract, you do it in order from left to right. Don't add 15 plus 12. Take 15 minus 4 and you get 11. Wait. Oh, this is a negative 3. Negative 15 minus 4 is negative 19 plus 12. And that would be negative 7, which does equal negative 7. I was worried for a minute there, but I just forgot my negative. So the first one checks, and then you would do the same thing to check the next two. All right, moving on quickly. So you can see that there's more than one way to do these problems. There's multiple ways. This is a business application, so just to show that there is times in real world where you would do a 3 unknowns, three equations, 3 unknowns type of a situation. This one shows the different types of tickets sold, where you could sit, the orchestra, the mezzanine, or the balcony, and what they sold on 3 different days, and then what their total sales were. You could use those to find how much each seat cost. So you would write your system of equations, you'd write one for each day. And the X is one place you could sit. I think that was the orchestra? And so we're letting X be orchestra, Y be mezzanine, and Z be balcony. And you can write 3 equations to show how much you sold each day. And there's no Z in the last one because they didn't sell any of that ticket amount on that day, on Sunday. It might be a good idea to put plus 0Z as a placeholder when you do this. If you ever come across that, then write that variable, but just put a Z in front of it so you don't forget that that is an option. So I'm going through this rather quickly, but you can pause the video and look and see how these ones were solved in order to solve for, first they solve for Y, and then they solve for X, and then they used X and Y to solve for Z in one of those original equations. And since it's a word problem, you should go back and see what it makes sense for the answer. All right, here's what I want to spend a little more time on. The examples that we did already had one unique solution. However, we looked at what the meaning of three planes intersecting would look like, and we know that sometimes there might be no solution and sometimes there might be an infinite number of solutions. Consistent means that you have at least one solution. So we need to say if it's consistent or inconsistent and determine the number of solutions. The number of solutions will be one solution, no solutions, or infinitely many. So to do this, we just start solving the equation. So we go through and first of all, it's x, y, z in each of them. Yep. And we need to see what variable we could eliminate. When you look for what you can eliminate, remember that the problem that I made easier by division, check and see if every term of one of your equations is divisible by the same number. It can quickly result in a simpler equation that might be easier to work with. So I see that every term of this first equation, number one equation, is divisible by 2. If I divide every single thing by 2, I would have 1x minus 3y plus 2z equals 1. I'm dividing everything by 2. It's an easier problem to work with. Let's check and see if the second one can also be divided by anything. They're all a multiple of 3, so I could divide each of these by 3. And that would give us negative 1x plus 3y minus 2z equals negative 1. See how much simpler these equations are? And then the third one are all multiples of 5. I could divide each of these by 5. And that would result in the simpler equation of 1x minus 3, minus 3y plus 2z equals 1. Right away, I notice something now. The top equation and the bottom equation are exactly the same. The middle equation is the same, except all the signs are opposite. What does that mean? That means that all three of these, they're going through the longer method here. Has an infinite number of solutions. That's what it means. So let's look back at our examples. How could we tell that from our equations? If we add the first two together, we would get x minus 1x is 0. Negative 3y plus 3y is 0. 2z minus 2z is 0. Equals 1 minus 1 is 0. Let's add the bottom two together. Negative 1x plus 1x is 0. 3y minus 3y is 0. Negative 2z plus 2z is 0. Negative 1 plus 1 is 0. We get a true statement for any combination of adding these together. So then the answer is infinitely many solutions. It would be those three planes intersecting at one line. So there's going to be infinitely many solutions. They did it using the original numbers, and they got the same answer, even though it took them more work to do it. They still got that 0 equals 0 when they added those two, and when they added 1 and 3, they had to do some multiplication first. They also got 0 equals 0. Therefore, it's an identity. It's consistent. If they ask you to classify it as inconsistent or consistent, it's consistent because it does have at least one answer, but it also is dependent, and it has an infinite number of solutions. Let's look at another example. First of all, I'm going to see, is there anything, no, I can't make this one simpler. There's no common multiple that I could divide each of these by. This one I could, though. I'm going to divide every one of these terms by 2. Let's see if that makes it even simpler than it already looks. So I have changed this equation to this just to make it quicker to solve. All right, so now I have, Note too that in this one there's no x term, so I'm going to write 0x here. Oh, it won't let me do erase anymore. 0, no, stop that. 0x plus y minus z equals -2. That was the last one, so that these are all lined up. All right, I want to eliminate I'm going to eliminate the y term. I'm going to multiply, or not multiply, I'm going to add number 1 and number 3 together. So I would have, should I rewrite them? 2x minus y plus 3z equals 6, and the bottom one was 0x plus y minus z equals -2. If I add these two together, I get 2x plus 0x is 2x. Negative y plus y, the y's cancel, plus 3z minus 1z is 2z equals 6 minus 2, or 6 plus -2 is 4. So that's a much simpler equation. Now I have to combine two others to eliminate the y term. I will use the top two. So I'm going to combine these two to eliminate the y term. So I'm going to have to do a little bit more work on this one because I don't have it set up for elimination yet. But they're pretty short little equations, or low numbers, so it should be all right. In order to eliminate the y term, I need a plus 2y and a minus 2y. So I'm going to multiply the top one by a -2, because that will be -2 times -y will be a plus 2y like I wanted. And I'll write that new equation down here. So I have -2 times 2x, that would be -4x. -2 times -y would be a plus 2y. -2 times 3z would be -6z. And then I have 6 times -2 is -12. And now I'm going to have my two new, these two, I'm going to work with these two. Add these two together. 1x minus 4x is -3x. -2y plus 2y is 0. Cancels. 3z minus 6z is minus 3z. And 5 minus 12 is -7. All right, so now I've got these two equations to work with. I have a new system of linear. Oh, that color's going to be too light. I'll use black. And I'm just going to solve this system. I want to keep my work on the same page, so I'm going to leave it here. I have an x and a z in both of them. And this is -3x minus 3z equals -7. So I can either use substitution or elimination to try to solve these. I could multiply them so that they both have 6 as a coefficient. That might be one way to go. Or I could use some substitution. The top equation looks pretty easy to solve for x. Let's go with elimination again, though. Let's make them both be 6x and -6x. So the top one needs to be multiplied by 3. And the bottom one needs to be multiplied by 2. All right, so on the top I would have 3 times 2x, that's 6x. And then I would have 3 times 2z, that's 6z, is equal to 12. And then on the bottom equation, I would have 2 times -3x, that's -6x. And 2 times -3z is -6z. And 2 times -7 is -14. Well, this is interesting. 6x minus 6x is gone. It's 0, which I wanted, but also the z terms are going to eliminate. So I'm going to get 0 equals -2. But 0 does not equal -2. This is false. So then you know that there is going to be no solution. When you get a statement that is false, you get no solution. And we can't go back and try to find, what is x or what is y. You can't, because there's no solution. At this point, you know then that these three systems would never intersect at a point. This is just another, or this example continued. I'm going to go through it quickly because we already did it. I want to get to the next one. So here's their answer was also no solution, but they solved it a different way. Okay, so that's it. And several of these examples that I did are on your worksheet, so that should save you some time if you are filling that out while you're watching and being able to do it that way. All right, so thank you very much. Have a great day, and let me know if you have any questions.